Hello and welcome back to this series on how computers actually work. Now, before we get into the details of the circuits which make a computer do what it does, we've got one more Boolean operation that we need to look at today. One more bonus logic gate. Now, if you haven't seen the last video, you're going to want to have watched that first because today's video relies heavily on the knowledge from that one. You can probably watch that by clicking here somewhere. That's on logic gates, and you're going to need to know how logic gates work in order to understand today's video because we're going to be building very heavily on it. Okay, so if you've seen the last video, you're confident on logic gates, then we can go on to look at our final logic gate, our final algebraic Boolean operation today, which is XOR, which is short for exclusive OR. Okay, so let's take a look at the truth table for XOR. XOR takes just two inputs and returns true only when one or the other input is true, but not both. So it's true if input 1 is true and input 2 is false, or if input 1 is false and input 2 is true, but not if both are true or both are false. This is where the name exclusive OR comes from. It must be exclusively one or the other. So you can think of this XOR operation as OR but not AND. And that should give you a pretty big clue about how we're going to construct the logic gate for XOR. We're going to use the other logic gates. We're going to compose them into a circuit to do this XOR check. Before we look at building an XOR gate, we need a way to represent the gates we've already looked at. Fortunately for each one, there's a standard symbol for representing the gate. And as always, my first attempts to draw these went terribly. These symbols are industry standard and they're pretty simple, so they're not too difficult to remember. This first one is an AND gate with its two inputs on the left, its output on the right. And it's in the shape of a capital D, just like the last letter of AND. So it's not too difficult to remember that one. Next we have our OR gate, again with its two inputs on the left hand side. And it's drawn, I like to think of it a little bit like a cartoon rocket with its output on the right. That's the OR gate. And finally our NOT gate, which is an equilateral triangle with a circle at the output point. It's two inputs on the left. And that's our NOT gate. I'm not actually sure who came up with these symbols, but they're the industry standard and we'll be using them for the rest of the video as we build our XOR gate. So if you remember earlier, I described XOR as OR but not AND. And that tells us everything we need to know because that sentence contains all three of the logic gates we know how to build already. So that's exactly what we're going to do. We're going to use those logic gates to compose XOR. We can break down the requirements of XOR into two checks. We can first check whether at least one of our inputs is true. For that we can use an OR gate. OR will return true if at least one of the inputs is true. The second check that we need to do is to check whether both inputs are true. This can be done with an AND gate, which will return true if both inputs are true. Now, if both inputs are true, then the XOR needs to fail. So we actually want to return true if the AND is false. To do that, we can invert the output of the AND gate with a NOT gate. So at the top, we get a true result if at least one input is not true. And on the bottom, we get true as the result if at least one input is true. So these are the conditions for XOR. By ANDing these two paths, we know two things: that at least one input is high and that at least one input is low. So if the result of this final AND is true, we have satisfied XOR. And this is how we draw the symbol for the XOR gate. You'll see how comparable it is to the OR gate that we looked at earlier. Remember how we made all of the logic gates last time using transistors? Well, as we start to do more complex things using more and more transistors, we no longer want to have to fiddle around with individual components. Instead, we want to step away from that complexity. We just want that logic to work when we need it to. This is called abstraction, and it's one of the most important ideas in computing and computer science. Replacing our messy drawings of logic gates with symbols is a form of abstraction. We know what it means, but we don't need to think about it anymore. Today, instead of building AND, OR, and NOT gates from scratch, we can abstract them away by using pre-made integrated circuits instead. So let's take a look at the chips that we're going to be using. This is the datasheet for the 74LS04 made by Fairchild Semiconductor. It's a NOT gate. You can see on the diagram that this chip contains 6 NOT gates, taking input on A pins and outputting on Y pins. We can see the inverting function in the truth table, where A pin is high, Y pin is low, and vice versa. And this is what the 74LS04 looks like. The next chip we need is the 74LS08, an AND gate chip, again made by Fairchild. It contains 4 AND gates. Input is taken on B and A pins and outputs on Y pins. As the truth table shows, when A and B are both high, Y is also high. And this is our 74LS08 chip. And finally we have the 74LS32 OR gate, made by Fairchild. This chip contains 4 OR gates. Each takes input on A and B and outputs on Y. As you can see on the truth table, if either A or B are high, Y is also high. And this is our 74LS32 OR gate chip. To begin with, we have an OR gate set up here. This is the OR chip we looked at. This red light is the output of the OR gate, and we're ORing these 2 buttons. When either of them is high, the OR gate outputs high on the red light. We've now added the AND chip, outputting on this red light here. We're taking inputs from these 2 buttons again, and when both are high, the red light turns on, the output is high. We've now added this NOT gate chip, outputting to this yellow light. It's taking input from the AND gate as shown by the red light. So when the red light is off, the yellow light will be on. When one input is high, the OR gate is high, and the AND gate is low, therefore the NOT of the AND gate is high. When both are low, the OR is false, although the NOT of the AND is true. And when both are true, OR is false, but AND is also true. Therefore, the NOT of our AND isn't. And lastly, we've got this final AND gate with the output connected to this green light here. One of the inputs comes from the OR output of the inputs, and the other input is from this NOT, the yellow light here. And this green light represents our XOR output. When one input or the other input is high, both the OR and the NOT of the AND are true, and therefore the green light comes on. Notice that when both are false, OR is false, so NOT is true, and therefore the green light is off. And when both inputs are true, AND is true, therefore the NOT is false, and the green light again stays off. And that is our XOR logic gate circuit. And that's our fourth bonus logic gate, Xor, composed of the other three logic gates. And this is a pattern that you will see more and more as we continue our journey into how a computer works, taking these small, reusable pieces and using them to complete different functions. And Xor is a particularly important logic gate, and we'll see a very useful use for Xor in the very next video as we compose one of the most important circuits in all of the computer. As always, I want to hear your thoughts and questions down in the comments. Anything that you want to know or anything you want me to know, write them down there and I'll be sure to get back to you. I'm pretty excited for this series as we discover how a computer really works from the very bottom up, from the electrical foundations. So make sure that you don't miss a video by clicking subscribe and turning on notifications down there. This is 54M, and I'll see you soon.